Another algorithm we will talk about today about in a heuristic search technique is A** search algorithm, right? So what is the A** search algorithm in a heuristic technique, and why we are need another domain or another heuristic technique? For what purpose the A** search algorithm is used, or what is the A** search technique simply? So A** search, we have discussed about the best first search, we have discussed about the depth first search, BFS और DFS हमने बेस्ट फर्स्ट और द DFS हमने डिस्कस किया BFS and the DFS, and now we are discussing basically the combination of both. We are discussing the A** search algorithm, which is a combination of a BFS and the DFS, and this is the algorithm which is a search algorithm that finds the shortest path between the 2 points. And definitely, when we are talking about the shortest path, we are using this algorithm for graph traversal and pathfinding. So what will be the steps we will talk about here? We will talk about the steps according to a example also. So when we say how it works like it starts with a starting node, and it finds a or build a path in form of a tree from the starting node, and then extend the path from one edge at a time. And with the help of, as it is a search technique under the heuristic search technique, it uses the heuristic function to estimate the cost of reaching the goal from each node first, and then prioritize the path which have a lowest cost, and continue with the lowest cost, and continue till the when the goal node is reached. So what is the motivation? To approximate the shortest path in the real-time situations like in a maps game where there can be any hindrance, can be many hindrances. So here we use the A** search approach here. As we can see here, a picture here, we can consider 2D grid here having several obstacles which are shaded one, and we start from a source cell which is colored as a red cell, and we need to go to the goal cell which is the green cell here. So how it works? Let's discuss. So we know the goal state. So what is the A search algorithm? It is one of the best and the popular technique used in pathfinding and the graph traversal. Why we use the A** search algorithm? Informally speaking, A** search algorithm, unlike the other traversal techniques, it has a brain, right? Why it has a brain? Because it works on the lowest cost nodes. What it means is that it is really a smart algorithm which separates it from the other conventional algorithm. The fact is clear, as it is mentioned that in the many games, it definitely use this algorithm to find the shortest path very efficiently, or the approximate shortest path. That's why we are saying that it has a brain. So how we will move from red node to a green node here? So we had consider a square grid having many obstacles, and we are giving a starting cell, as I had shown you a figure in which the red cell is the initial state and the green cell is the goal state. So we are having a static cell and the target cell. We want to reach to our target cell, if possible, from starting cell as quickly as possible. So our task is to find the shortest path between the starting cell to the goal cell. So here the A** algorithm, what A** algorithm does is that at each step, it picks the node according to the heuristic function, right? Which is the parameter equal to the sum of the two parameters G and H, and each step it picks the node and the cell having the lowest heuristic function here. And what is a G? The movement cost, right? We are talking about the three variables here, f, g, and h. F is the heuristic function here, right? And g is the movement cost to move from starting point to a given square on the grid, following the path generating to get there. And h is the estimated movement cost to move from the given square on the grid to the final destination, right? Here we are talking about the final destination. And this is often referred to as a heuristic, which is nothing but a kind of a smart guess that we can reach to this goal state or at the final state from this to this at this cost. So we really don't know the actual distance until we find the path. We just making our guesses. And because all sort of the things can be in a way, the water, the wall, any obstacle can be there. There can be many ways to calculate the h here, the heuristic value. Suppose, as in a figure, we want to reach to a target cell from the source cell, then the A asterisk algorithm would follow a path. Now, what path we are talking about here? By using the equilibrium distance as a heuristic. So first it will use the approach as a equilibrium distance as a heuristic here. So here basically it will move from the red to a green, right? And unblock are the white one blocks, gray one are the blocks, red one is a target, and green one is here the source. So what the A asterisk search algorithm will use, the A search algorithm makes the most intelligent choice at each step. Hence you can see here the algorithm goes from 4, 2 to 3, 3 and not 4, 3 shown by the cross. Why? Because it is using the diagonal approach. It is using the lowest cost here. It has saved is moving the one block here from 8 to 1. First it will move from 8 to 4 and then by moving from 4 to 3 it will move 4 to 2 right here. So it will move from, it will not move from 4 to 3 here, it will go from 3 to 3 here, right? So here we are talking about the similar, the algorithm goes from 3 to 3 to 2 to 2 and not 2 to 3 shown by a cross here. So it will not move to 4 to 3 here first, right? And then it will move again 3 to 3 here, right? So it is basically using some diagonal approach, right? Which can be which it's using that in between it can skip the blocks and simply it is searching for the shortest path to reaching to the source state here. So how the heuristic, what are the heuristic? We can calculate G, but how to calculate the H? We can do this, either calculate the exact value of H, which is certainly a time consuming, or we can calculate the approximate value of a H using some heuristics less than consuming. So how the exact heuristic will be calculated? We can find the exact value of a H or the heuristic, but this is generally very time consuming. Why? We need to pre-compute the distance between each pair of a cells before running the A asterisk algorithm. So if we need to find the exact heuristic value or the exact value of a H, then we need to pre-compute the distance between each pair of a cells before we need to start the A asterisk algorithm. And if there are no block cells or obstacles, that can be just find the exact value of h without any pre-computation using the distance formula or the equidistance. So if the blocks are there, if the obstacles are there, it will be difficult for us or it will be very time consuming to calculate a exact h. So what are the approximate edge and what approaches we use in the approximate edge for finding the approximate edge? We have discussed in the 8 puzzle problems about the Manhattan distance also. There are 3 approximation heuristics to calculate. First is the Manhattan distance. It is nothing but sum of the absolute values of a differences in the goals x and y coordinate and current cells x and y coordinates respectively. So here we are talking about the absolute values here. So when we use the heuristic, when we are allowed to move only in a 4 direction, right? When we have discussed this kind, the 4 directions in a 8 puzzle problem also. So when we use this heuristic, when we are allowed to move to a 4 direction, right, left, top, bottom, and the Manhattan distance heuristic is shown by here when we are talking about from source to a target, right? So this is the heuristic before without any obstacles. Then the diagonal distance, we need to find the diagonal distance, also another approximation we can find with the help of a diagonal distance. So it is the maximum absolute value of difference in the goals xy coordinate to the current cells xy coordinate respectively, right? So here we are talking about the maximum absolute value just. So here we are talking about the maximum absolute value where we can see here d is the length of each node, right? Usually 1, and due to d2 is the diagonal distance between the each node by usually the square root of 2 here. So when we can use this heuristic when we are allowed to move in a 8 directions only similar to a move of a king in a chess. So when we are talking about a chess game here, we can use a diagonal distance heuristic, and the diagonal distance heuristic can be like this also, right? So we are talking about the diagonal heuristic distance here. Now the equidistant distance, right? So equidistant distance is basically the distance between the current cell and the goal cell using a distance formula. So how we can use the current cell plus the current cell of a x and the y coordinate and the goal x and the y coordinate. So when to use this heuristic, how to use this heuristic, we are just calculating the square root of the differences of current x and the goal x coordinate. Then we are getting the distance, the difference between the distance of a current y and the goal y coordinate, and we are getting the square root, and we calculate here the heuristic value of the heuristic function here. When to use this heuristic? When we are allowed to move in any direction. We are allowed to move in any direction, then we are using the equidistant distance. So there are three approaches that we have discussed in the asterisk approach. What three approaches we have discussed? First is a Manhattan distance, then the diagonal distance, and then the Euclidean distance here. So diagonal is there. So relation, what is the relation between the similarities and the difference with the other algorithms here? So here the Dijkstra is a special case of a asterisk search algorithm where when we are talking about where h equal to 0 for all nodes. So how we can implement here? So how, what is the best path finding in the asterisk algorithm? So what kind of a data structure we need to use and how we can implement this algorithm in the Python or the C++, right? So how to implement, we can use any data structure to implement open list and the closed list. But for the best performance, we can set the data structure of a C++, implementing the red, black, tree and the Boolean hash table for the closed list. So here we are talking about what is the best way of implementing a asterisk search algorithm. So then what are the further application of a asterisk algorithm and what is the basically the time complexity and how you find the time complexity and what is the time complexity? Can anyone tell me about the time complexity also? I had allowed the mics of everyone. So what is the time complexity? Because for each and every algorithm you
Time
need
taken by any
to
algorithm
define.
or execute.
So how we will define
Time
here the
taken.
time complexity?
How much time?
How much time is we are getting from going from source node to a goal node? And when we are talking about in form of a tree, we are talking about the time complexity in form of a vertices and the edges. Here we are talking about the time complexity of a asterisk algorithm. How we can define here the time complexity of a asterisk algorithm. We are talking about, when we are talking about in form of a trees, what we say, we talk about B and the D. We have seen about the time complexity of uh, BFS and the DFS also. Here we are talking about the time complexity of a asterisk algorithm. Like when we consider any graph, right? So what we are talking about? We are talking about simply the branches and the D. B is stands for the branching and the D stands for the number of the nodes on the path, right? So basically time complexity क्या find करता है? Time complexity is the quality of a history function which determines the time complexity, how much time it is getting to move from a goal node to a from a source node to a goal node, right? The terminal node that comes under the time complexity. Consider a graph. It may take us to travel all the edges to reach to a destination cell from the source cell. For example, consider a graph where the source and the destination nodes are connected by a series of edges like 1, 2, 3, right? Source is a 0 and then to the 1, then to the 3, and then 3 is your target. So the worst time complexity is OE, where E is the number of the edges in a graph. When we need to move each and every edge of a graph to move to a source to a target. So this is a worst time complexity. Or we can say that the number of edges will be moved, that will be the worst time complexity. So we need to move to a minimum edges to reach to a target, right? So that will be the best time complexity. So here the auxiliary space is there. In the worst case, we can have all the edges inside the open list. So required auxiliary space here. So the worst case is moving to the total number of the vertices here. We are going to the total number of the vertices. That is the space when we are talking about the worst space here. So what if the search space is not a grid or a graph? Then we are talking about it. So the same issues applies here also. The example of a grid is taken for the simplicity of understanding. So we can find the shortest path between the source node to a target node. And in a graph, when we are talking about, then again, when we are talking about a graph, in a graph, we are talking about the branches, we are talking about the nodes. So the moving to each branch from source to a target will be the worst time complexity here. So what will be the limitations? Although being the best path finding algorithm, because it is a combination of a BFS and the DFS. A asterisk search algorithm doesn't produce the shortest path always, as it relies heavily on the heuristic or the approximate value which calculates the edge here. So it will not give you the always the shortest path.